Okay, good afternoon, lads and ladies. Today is our start of our last week here in pre-calculus. So I want to congratulate you guys for hanging in here and for all the hard work you've done to get this far. We're going to change gears today. So the last few weeks, we've been talking about systems of equations and matrices and how matrices are connected to systems of equations. I have posted some resources for you in the modules on Canvas that I think you might want to take a look at. Make sure everything is where it should be so I can show you. Oh wait, they didn't go there. So where did they go? Did they go to the announcements? Live lecture, quiz study guide. Homework 12. I thought I posted some stuff for you. Maybe I didn't. So, oh yeah, there it is. Yeah, solving systems 3x3s. All right, here we go. So let me turn on my screen share. If you go to this announcement, video example solving 3x3 systems of equations, you can see here this I posted when we did that first homework set on linear systems, because I thought you guys might want to be able to watch more examples. But if you come down to these last two videos, Patrick JMT is using matrices and row reductions. This is the technique that I taught last week, which was the Thanksgiving week. So I think probably a lot of people missed class that week. If you missed the lectures on matrices and using matrix row reduction methods to solve a system, these two videos are your friend. I will post some more stuff about matrix algebra. So I'll post a separate announcement after I finish here today for people who want to review more of that. But ideally, you would just watch the video lecture from last Wednesday, which is up right here. So if you're looking for a little bit more help on the matrix homework, make sure you've watched this lecture from last Wednesday. I think there were only like 7 or 8 people here that day. So please do take a look at that if you haven't yet. And also look back at that older announcement with Patrick JMT. Another thing I want to talk about is the quiz and study guide 4. I didn't want to give you guys like too much to do in this last week because you're going to have that test, which is going to be a take-home. Exam 4 will be a take-home. I will give it out on Wednesday. I don't want to bombard you with too much stuff. So study guide 4, quiz 4 in WebAssign is open. It's been open for a few days now. But it's set up like a homework rather than like a quiz. So normally on the quizzes, I only give you guys a few options to solve each problem, right? Like I think I normally give you 3 attempts. Here, it's like a homework. You have as many attempts as you want. So make sure that as you go through this, you're paying careful attention to the matrix problems, giving it the love they really deserve. And then all of the new stuff is also in here. So today we're going to start talking about sequences and series. And rather than giving you a second homework set to talk about sequences and series separate from the study guide or the quiz, I just went ahead and put them together into a single assignment. So let's talk about sequences and series and summation notation. This is some of the coolest shit in all of mathematics. So I hope that you guys enjoy it. This, of course, is MAC1140, section 4. Today is the 30th. And today we're going to talk about sequences and series. So we can only go so far here. There's only so much time, but I could easily do a whole class on sequences and a whole other class on series. And it's worth doing, but not at this level. Here, our main goal is just to introduce the concept. What is a sequence? What is a series? And also the notation, right? Why do we use different notation for sequences? And what is that capital sigma thing that you see floating around in movies when they want to show scary math guy? So there's only one way to begin, and that's with the definition. A sequence is an ordered list of numbers. Right, like I'm sure you all have heard the word sequence used in practice. We talk about a sequence of things. There's a first thing, a second thing, a third thing, a fourth thing, and that list continues on and on forever. For us, the objects in the list will be numbers, but the fact that it's an ordered list is important. So a sequence is an ordered list of objects. Now, for us, they'll be lists of numbers. There are a bunch of famous sequences, like the sequence of prime numbers, the sequence of Fibonacci numbers, sequence of squares. We'll look at all of those. An equivalent definition, and these really are equivalent, they logically say the same thing, is that a sequence is a function whose domain is the natural numbers, aka the counting numbers. You know, 0, 1, 2, 3, and so on. Some people say this set starts at 0. Some people say this set starts at 1. It depends on basically whether you're from continental Europe or not. People from continental Europe include 0 as a natural number. People from the rest of the world do not. I am inclined to include 0 as a natural number, but our sequences are going to be functions whose inputs, domain, are just non-negative whole numbers. In other words, there's an output corresponding to the input 0, an output corresponding to the input 1, an output corresponding to the input 2, and so on. There is some special notation, but before we do that, I just want to look at a few examples. So the list 1, 3, 5, 7, 9, 11, 13, and so on, this defines a sequence. Now there's a pattern here, right? There's 1, 3, 5, 7, 9. These are all the odd numbers. The first term is 1. The second term is 2. The third term, I'm sorry, 2. The second term is 3. The third term is 5. The fourth term is 7, and so on, right? And I hope that you can see the sense in which this really does define a function. The input 1 goes to 1, the input 2 goes to 3, the input 3 goes to 5, the input 4 goes to 7. So the place you are in the list, first place, second, third, fourth, fifth, is the input. Could anybody tell me what the nth term would look like here? The trick is to find an explicit relationship between the number term you are and the output. So n plus 1 is a reasonable guess if we look at a couple guys like 2 goes to 3 under the n plus 1 map. 3 goes to 5 under the n plus 2 map. So Lily and Ronald are both giving, Brooks, Lily, and Ronald are both giving things that work in some cases. But does n plus 1 work for all of these? Well, is 1 plus 1 equal to 1? Is 3 plus 1 equal to 5? No, not quite. And similarly, while the n plus 2 seems to work here, 1 plus 2 isn't 1. 2 plus 1 is 3. 3 plus 1 is not 5. So neither n plus 1 nor n plus 2 work all the time. But what do you notice about odd numbers? What makes an odd number odd?
That they're only multiples or themselves in one.
That's what makes a prime number prime. But not all odd numbers are prime. For example, 9 is divisible by 3.
Oh, true.
So an odd number is a number that's off from an even number by 1, right? It's a number that's not divisible by 2. So 3 I can think of, 1 I can think of as 2 minus 1, 3 I can think of as 4 minus 1, 5 I can think of as 6 minus 1, 7 I can think of as 8 minus 1. And then what do you notice between this number and this number, this number and this number, this number and this number, this number and this number? If we look at one more, the 5th term, which is 9, is 10 minus 1. These are all 1 less than an even number. And the even number you get here by doubling the number term you are. So the nth term would be 2n minus 1, right? This is 2 times 5 minus 1, 2 times 4 minus 1, 2 times 3 minus 1, 2 times 2 minus 1, and 2 times 1 minus 1. So I'd say the nth term here is 2n minus 1. And this sort of pattern recognition is a great place to start looking at sequences. So yeah, Olivia and Brooks, I think, both had kind of a neat idea here. You double the input. So say for the 4th term, I double the input 4 and then subtract 1. For the 5th term, I double the input 5, that gives me 10, and then I subtract 1. And for the nth term, I am doubling the input n and then subtracting 1. So just a simple example of a sequence. The sequence of odd numbers can be described as the sequence whose nth term is 2n minus 1. And there's a special notation for this. We can describe the sequence 1, 3, 5, 7, 9, 11, and so on as the set of all things looking like 2n minus 1, so curly braces, 2n minus 1, where n is allowed to run from 1 all the way to infinity. So when I want to refer to the whole list as a single object, here's the whole list. If I want to refer to it as a single object that I can call upon, this is the notation. It's all of the numbers of this form as n runs from 1 to infinity. And there I get this whole infinite list in a single expression. And we use the curly braces for this, just like you do for a set in set builder notation. Okay, so just for fun, I'll leave this here for a second longer. I'm sorry, I'm moving too fast. Just for fun, I'm going to give you a sequence in this notation and ask you to list the first 5 terms. Okay? That's what we'll do next. All right. So let's list the first 5 terms of the sequence curly braces 1 over 2n, n from 1 to infinity. What is the first term? Good, 1/2. I get that by plugging in the input 1. So it's 1 over 2 times 1, which is just 1/2. The second term? Good, Leanne and Olivia both nailed that. What about the second term? Yeah, it would be 1/4. I get it by plugging n equals 2 in here. So this is 1 over 2 times 2, which is definitely 1/4. The third term would be 1 over 2 times 3, or 1/6. The fourth is 1 over 2 times 4, or 1/8. And the fifth would be 1 over 2 times 5, or 1/10. Now, what you notice is that this notation here is rather cumbersome. I don't like having to write first term, second term, third term, fourth term. So instead of that, we use a new notation. Usually, to refer to the nth term of a sequence, we write a sub n. So here I would say a1 was 1/2, a2 was 1/4, a3 was 1/6, a4 was 1/8, and a5 was 1/10. It's just a much more compact notation. And it's the same thing as function notation. You can think of this as like a of n, right? Just like f of x. It's the output from the sequence when you feed it the input n. So a1 or a of 1 is what you get when you plug 1 in for n. a2 or a of 2 is what you get when you plug 2 in for n, and so on. This notation, the subscript notation, just makes it a little bit easier to work with sequences in the way that we'll usually want to work with them later in calculus. I'd like to just get us a little bit more practice with the notation, play around with some things, and then I'm going to talk about a few special kinds of sequences. Okay. So let's say, find a formula for an in the sequence whose first few terms are maybe 3, and then 9, and then 27, and then 81, and so on. So this is a little trickier, but I have a feeling that you guys can do it. What do you notice about these numbers here? Again, we're looking for a pattern, just like we did in that very first example. It's not quite n cubed, but almost. If you switch the symbols around, yeah, I see. So 3 conjectures here, and they're all good. N cubed, 3n, and 3 to the n. Brooks is correct here. This is 3 to the n, and one way to see it is that 3 is 3 to the 1. 9 is 3 to the 2. 27 is 3 to the 3. 81 is 3 to the 4. To go from one of these to the next, you're multiplying by 3. So here I would say an is 3 to the n. It's kind of like an exponential function. These have a special name in the setting of sequences. They're called geometric sequences. And I'll show you why that's the case, and we'll talk more about geometric sequences in a little bit. Hell, let's Is there anything else I want to do? Oh, there's one other thing I want to do. Yeah, before we do that, I want to look at one other little thing here. First, any questions about this formula, how we get an equals 3 to the n out of this? It's really just a pattern recognition thing. 3 to the 1, 3 to the 2, 3 to the 3, 3 to the 4. Oh, okay. So in general, it's 3 to the n. Okay. Give us another sequence to play with here. And this time we're going to do something a little neat. We're going to graph the sequence. Just like you can graph any other function, you can graph sequence as ordered pairs, input, comma, output. So let's find and graph the first 5 terms of the sequence an equals -1 to the n plus 1 over n. This is interesting. We've got a kind of weird looking formula here with a power of -1, and then downstairs there's an n. Well, if I need to find the first 5 terms, I'll worry about the graph later. A1 is what I get when I plug in n equals 1. So that's -1 raised to the 1 plus 1 over 1. That's -1 squared over 1. And -1 squared is -1 times -1 is +1. So this is 1 over 1, or just 1. A2 would be -1 to the 2 plus 1 over 2, which is -1 cubed over 2, which is -1/2. A3 would be -1 to the 3 plus 1 over 3, or -1 to the 4 over 3. And -1 to the 4 is -1 times -1 times -1 is +1 over 3. Yeah, so the power of -1 here is n plus 1. And the parentheses are important. It's -1 being raised to the power n plus 1. A4 would be -1 to the 4 plus 1 over 4, which is -1 to the 5 over 4, which is -1 over 4. And A5 would be -1 to the 5 plus 1 over 5, which is -1 to the 6 over 5, which is +1/5. So the first few terms of the sequence are 1, -1/2, +1/3, -1/4, +1/5. Interesting. So you notice it flashes back and forth, positive, negative, positive, negative, positive. That's what the effect of this power of -1. -1 to the n, -1 to the n plus 1. As n runs over the counting numbers, that blinks back and forth between +1 and -1. And then downstairs, you just have an n, so the denominator is 1, 2, 3, 4, 5, and so on. The graph of such an object, the graph of any sequence, is just like graphing any other function. Your inputs are on the horizontal axis, so this would be the n-axis, and the outputs, an, are along the vertical axis. I'm going to mark this up here as +1, and this down here as -1. A1, I'll mark off 1, 2, 3, 4, 5 along my n-axis. A1, the output when I fed the input 1 was 1, so I have a dot up here. The point 1, 1. A2 was -1/2. So I'll have the ordered pair 2, -1/2, which is right down here. A3 was +1/3. 1/3 is like right here. So 3, 1/3 is a point on my graph. A4 is -1/4. So 4, -1/4 is on my graph. And A5 is +1/5. That's going to look like this. And you can kind of guess and see how the rest of these would look. You can kind of see a pattern. The next guy would be below here, but closer. Then above here, but closer. Then below here, but closer still. This is what the graph of a sequence looks like. It's just a collection of dots. Or points. And they're of the form n, an. Right? Input, output, just like for any other function. The difference between these and the functions you've graphed in the past is that there's no curve connecting them. It's just the dots. Why isn't there a curve connecting them? Because the inputs are only allowed to be whole numbers. So there's only a dot above any of the whole number values on the horizontal axis. Which means there's no way for these things to be continuous. There's no way for them to be like smooth. There's no way for them to be really a lot like any of the functions that we've studied in this class. They don't have, x-intercepts aren't really interesting. I can't talk about what happens nearby. There's no real meaningful notion to rates of change here, at least not at any particular finite value. So in calculus, what we end up studying for these are horizontal asymptotes. As n gets bigger and bigger and bigger and bigger, are these outputs getting closer and closer and closer and closer to something? That's the calculus operation we like to do on these. And you'll do lots of that at the end of Calc 1 and also the middle of Calc 2. But for now, my goal is just to get you comfy with the notation and the concept of the graph. Do we see where the points on this graph are coming from? Are there any questions about these? So this was the ordered pair. I'll come back and label these 1, 1, 2, -1/2, 3, 1/3, 4, -1/4, 5, 1/5. So those were the ones that we were asked to graph. Sequences which blink back and forth, positive to negative to positive to negative to positive to negative, like this, are called alternating sequences. I'll leave this here for just another second or so, but then we're going to move on and talk about two special kinds of sequences. So the first special kind of sequence I want to talk about is a geometric sequence. So a sequence is called geometric if there is one constant that you can multiply by to move from any term to the next term. For example, that 3 to the n sequence we saw a while ago, an equals 3 to the n is geometric because a1 is 3, a2 is 3 squared is 9, a3 is 3 cubed is 27, a4 is 3 to the 4 is 81. And to go from any given term to the next term, we're multiplying by 3. So the next term would be 81 times 3, which would be 243. And you could continue on like that. That constant that special constant is called the common ratio. And we write it as a lowercase r. So here, this is geometric, and the common ratio is r equals 3. Questions about what it means for a sequence to be geometric? Okay, I'm going to look at another example here.
Do the other sequences that don't have that aren't geometric, do they have like another name? Like are they like linear or what?
There is a special name for a bunch of other kinds of sequences. There are arithmetic sequences, recursive sequences, and lots of other types. But
Okay.
for now, we're just going to look at geometric and non-geometric sequences.
Okay.
So let's look at this guy. Can we find a formula for the nth term?
Aren't these supposed to be natural numbers?
The outputs do not have to be natural numbers, only the inputs.
Okay.
Outputs can be anything you want. But is there a pattern you notice here? To go from 3 to -2, we're multiplying by -2/3. And if you multiply -2 by -2/3, that'll give you +4/3. And if you multiply that by -2/3, that'll give you -8/9. So this appears to be geometric. With common ratio -2/3. Now, if you compare that to our last guy, an equals 3 to the n, here the common ratio was 3, and the formula for an was just 3 to the n. So we might guess that an is something like -2/3 to the n, because every time we're moving from one term to the next, we're multiplying by another copy of -2/3. Now, of course, this doesn't work, right? If you plug in n equals 1, you don't get 3. If you plug in n equals 2, you don't get 2. But if you slap on a constant here, 3, and then you say n starts at 0, this will work. Try it. A0 would be 3 times negative 2/3 to the 0. Well, negative 2/3 to the 0 is 1, so that's just 3. A1 would be 3 times negative 2/3 to the 1. That's 3 times negative 2/3, that is negative 2. A2 would be 3 times negative 2/3 squared. Well, that's 3 times positive 4/9. That is indeed 4/3. So this works. And in general, geometric sequences can be written as an equals some constant, I like to call it A0, times r to the n, where n starts at 0. For geometric sequences, it's nicer to let n start at 0, because that way you can use this formula. No, I'm sorry, guys. I've been drinking a lot of coffee. I need to run to the bathroom. I will be right back. Okay. Sorry, thank you for your patience. All right. So what we've discovered here through this example with a little bit of help is that this particular sequence, 3, -2, +4/3, -8/9, can be written in this way. It's 3 times -2/3 to the n, where n runs from 0 all the way up to infinity, just taking natural number values. And the more general result here is that any geometric sequence can be rewritten in this way. Or if you insist that n starts at 1, you can write this as that same constant a0 times r to the n minus 1. Just shifting everything back, where n is 1, 2, 3, and so on. And these formulas for geometric sequences are nice. They're helpful. We'll have one more class Wednesday, but yeah, we are getting there. It's almost over. It's almost over.
Wait, I have a question.
Sure.
Where would you have gotten the -2/3? Like if you were like looking at 3, -2, 4, 3, like if you were looking at that, like on like for example, if you're just like looking at it, trying to figure it out, like where would you like think, oh,
This one's a little
-2
bit
there?
tougher, but if you compare this guy to this guy, I think that's sort of the giveaway. So that to go from here to here, I notice the top is a power of 2, right? 2, 4, 8.
Right.
The bottoms are powers of 3, 1, 3, 9. So I'm thinking that the common ratio is something like 2/3, because to go from here to here, to change a 4 into an 8, you multiply by 2. To change a 3 into a 9, you multiply by 3. And then to deduce that it's negative, you can just see that the signs are flipping. Now, another way to do this, the reason we call it the common ratio, is you can divide any given term by the term that came before. So if you know for sure that your sequence is geometric, then if you divide this by this, you'll get this. And that's one reason we call it the common ratio. Like A3 divided by A2 is going to come out to -2/3. Or A2 divided by A1 would come out to -2/3.
Right. Okay.
Remember your guys' class, this is, I'm not losing my brain here, right? This is MAC1140. Yeah, your guys' exam is a take-home exam. I'll be giving it out on Wednesday. But the exam is not in class on Wednesday. It's going to be a take-home that I'll distribute on Wednesday. So we're going to have a class meeting on Wednesday.
Oh, okay. So like I get it. So you could just divide like 4/3 divided by -2 and you'll get the R term. Okay.
Exactly. Yeah, that's why we
That's
call it
easy
the
enough.
common ratio, because if you divide any 2 consecutive terms, they'll always come out to the same number. So it is a ratio that is common to any consecutive pair.
Okay. Perfect.
All right. There's one other kind of important or somewhat important family of sequences that I want to introduce you guys to, and those are called arithmetic sequences. Oh, so a take-home exam in this setting means I'll post the exam to Canvas. You'll download it. It'll be a PDF. You'll print it and write your solutions on that test and then scan those back into me. Or you can write on your own paper. Just make sure you write the problems and your solutions and then scan it back in. I'll be giving it to you on Wednesday. You'll be able to work on it until the start of the final exam. So when I post the exam on Wednesday, I'll post very detailed instructions. I promise there will be no uncertainty about what to do. But yeah, I'll be posting the exam. It'll be a PDF, download, and you can either print or write on your own. And then you'll write solutions, take pictures, upload. And the dates will be set in those instructions. All right. So yes, still we will have a regular class on Wednesday. Just at the end of that class, I'll be posting the test. All right. A sequence is called arithmetic, like arithmetic, only for whatever reason we emphasize the weird syllable, arithmetic, provided we can go from one term to the next by adding a fixed constant called the common difference. which is denoted by the letter little d usually. So an arithmetic is kind of the addition version of a geometric sequence. An arithmetic sequence is one where you go from one term to the next by adding a fixed constant. An example of one of these is the sequence we looked at earlier, the sequence 1, 3, 5, 7, 9, 11, so on. This is arithmetic. Because to go from 1 to 3, we added 2. To go from 3 to 5, we added 2. To go from 5 to 7, we added 2. And so on. To go from any term to the next term, we add 2. And here we notice that we can write this, the nth term here, as 1 plus 2n. If you allow n to start at 0. Or if you want n to start at 1, you can write it as 1 plus 2 times n minus 1. And this was the formula we came out to last time. We had 2n minus 1. If you simplify this, distribute the 2 and combine like terms, you get 2n minus 1. In general, well, let's look at another example before we do that. So another arithmetic sequence, we could say it would be like 3, and then 7, and then 11, and then 15, and then 19, and so on. What is my common difference here? So this first guy was arithmetic with common difference d equals 2. Just to go from 1 to the next, we added 2. Yeah, here to go from 1 to the next, we're adding 4. 3 plus 4 is 7. 7 plus 4 is 11. 11 plus 4 is 15. It's crucial that it's not just to go from 3 to 7, but also 7 to 11, also 11 to 15. You have to be able to go from any given term to the next term by adding that same constant. That's what an arithmetic sequence is. Now we have a kind of cheat code here. If I want to write down a formula for an, I can use this same sort of recipe here, right? An, I could say, is 3 plus n copies of 4, or 3 plus 4n. And this is where n is going from 0 on. This a kind of looked a little weird, but yeah, that's just an an. And you can check. If you plug in 0, you get 3. So this would be a0. Plug in n equals 1, you get 3 plus 4. This is a1. Plug in n equals 3, you get 3 plus 8 is 11. And so on. It works great. So in general, an arithmetic sequence can be written sorry, my pen is dying, as an equals a constant, I'll call it again a0, plus the common difference times n. And this is where n starts at 0. If you want to insist on n starting at 1, then you can write it as an equals a0 plus d times n minus 1. So these formulas for arithmetic and geometric sequences, they're somewhat useful, especially the formulas for geometric sequences. The thing I'd like to call your attention to is that arithmetic sequences, these are linear functions of n, right? And if you looked at the graph of an arithmetic sequence, those dots would all live along a line. If you look at the graph of a geometric sequence, those dots will all live along a curve that looks like an exponential function. So geometric sequences are the sequence version of exponential functions, And arithmetic sequences are the sequence version of linear functions. It's good stuff, right? So just getting used to the notation and the terminology. Oh, yeah, A0. Oh, well, you just have to have a name for this constant. I choose to call it A0 because it's the starting term of the sequence, and I like to start my sequences at 0. So I would call 3 here. I would call this guy A0. I would call this guy A1. I would call this guy A2, A3, A4, and so on, because that's the naming preference that I like. But you could call this C if you wanted. You could say C plus D times N, where C is a constant. All that matters is that this is some constant plus the common difference times N. Right. Right. Yep. And because I prefer to start my sequences with 0, this formula makes the notation look really nice, just really clean. I like it. But you don't have to. And I think your book actually has some alternate notations if you prefer to look at those. They, for whatever reason, force the sequence to start at 1, so they'll give you some version of this formula. But yes, that's the starting term, and then n times the common difference, or n minus 1 times the common difference. Okay, a quick word on what's called convergence. Suppose I give you the graph of a sequence. And let me just, I'm not going to give you a formula or anything specific. I'm just going to draw some pictures. So I'll add in here this horizontal line as a dashed line. Consider this graph. You don't even have to draw it. I just want you to think along with me. So maybe A1 is here, and A2 is here, and A3 is here, A4 is here, A5 is here, A6 is here, A7 is here, A8 is here. And the terms of the sequence just keep getting closer and closer and closer to this horizontal line L. This is what it looks like to say AN is going to L as N is going to infinity. As you go further and further this way, the dots are getting closer and closer to the line y equals L. The term used here is converge. We say that the sequence is converging to L. Converge means to come together. So here, all of these dots are starting to pile up on the same y value. It's a concept that's going to be very important in Calc 2, but you won't address much between now and then. So we don't go any deeper in pre-calculus than this, but it just means meaning, and I'll put this in quotes, AN gets closer and closer to L as N gets bigger and bigger. And it's very similar to finding a horizontal asymptote for a function, right? We talked about horizontal asymptotes using the same sort of notation, saying y goes to 5 as x goes to infinity, that sort of shit. This concept is very important for sequences because, among other things, it's what lets us define this idea of an infinite series. And that's what I want to prime you for as we move out of today. So the next thing I'm going to do is going to be a total change of gears. We're going to talk about summation notation next. So I just want you to have this picture in your head of something getting closer, a sequence getting closer and closer to some value as you go further and further along. So summation notation and infinite series. How many of you have seen this symbol before? The capital Greek letter sigma here is what this guy is. You may not like how I draw mine in general. Capital sigma, right? Looks like this. You've probably seen it, if nowhere else, on like fraternity houses and stuff. Here, what this is a shorthand for an addition problem. I think the easiest way to get comfy with it is to just look at an example or two. So what this says is sum 1 over n from n equals 1 to n equals 5. That's the way we would read this. SUM there, meaning add up. So in other words, we're going to take this thing, this sequence that's inside here, 1 over n, and add up all of those terms as n goes from 1 to 5. So that's 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5. And if I want to figure out what this is, I can have a common denominator and add it all up. This is called summation notation. Generally, or in general, sigma from n equals a, I should say, how do I do this without making it confusing? Let's say from n equals 1 to capital N of a sub little n is a1 plus a2 plus a3 plus all the way out. The second to last term would be a sub capital N minus 1, and the last term is a sub capital N. So what this notation here is, it says take this thing, an, whatever is here, and add it up as n goes from whatever is down here to whatever is up here. It's just a shorthand for a big addition problem. And the goal here is to get to a place where we can maybe start understanding what it means to add infinitely many things together. That's one of the big challenges with calculus, is wrapping your head around infinity. It's not an easy thing to do. I want to get a little more practice with the summation notation, and then I'm going to show you how to sum an infinite series in one special case. So suppose I wanted to compute the sum from n equals 2 to 6 of n squared. That means I'm going to take these things and add them up as n goes from 2 to 6. So in other words, that is just shorthand for 2 squared plus 3 squared plus 4 squared plus 5 squared plus 6 squared, or 4 plus 9 plus 16 plus 25 plus 36. So I'm not sure what this is off the top of my head. This is 13. 13 plus 16 is 29. 29 plus 25 is 34. No, it's not 34, 54. And 54 plus 36, let's see, 4 plus 6 is 10, so that's 60 plus 30 is 90. Did I do that right? We'll double check. I don't trust my arithmetic skills at all. 4 plus 9 plus, oh, I hate this calculator. Plus 16 plus 25 plus 36. 90. Oh, yeah, we did it right. Okay, good. Okay. I had my doubts. Don't worry if you had your doubts too. It's all right. So if we were summing from 1, it would be 91, right? Because I'd have a 1 squared at the start. Do we feel comfortable taking something like this and writing it out like this? Are there any questions about how we go from here to here?
Where'd you get the 2, 3, 4, 5, and 6 from?
So this says take this thing and add it up over these values of n. So the capital sigma says perform the addition problem that you get when you plug in for n all of the values between 2 and 6. So the 2, 3, 4, 5, 6 came from the n equals 2 to 6 here. Right? You can read this as like n equals 2 to n equals 6. Sum this from n equals 2 to n equals 6. So when I plug in 2 for n, I get 2 squared. The next thing would be 3. The next thing would be 4. And I stop when I get to 6. Does that make sense?
Yeah, it makes sense. Thank you.
Okay. A fun example to work with here. So here's our long-term goal. How can I make sense of an infinite addition problem? I'm going to give the thing a name. I'm going to call it S. I don't know the first. I know the first term was 2 squared because this down here says start at n equals 2. So I plug in n equals 2 for my first guy, and then I plug in all the n values between 2 and 6 and add them up. So I know that this first guy was 2 squared because this is a 2. You plug in n equals 2 into this, you get 2 squared. So I'm going to look at a slightly different one now. I'm going to look at 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32 plus, and so on. But I want to let it go on and on and on forever. So the addition problem is infinite in length. This is actually a horrible joke around this that goes, an infinite number of mathematicians walk into a bar. The first one says, give me a beer. The second one says, give me half a beer. The third one says, give me a quarter of a beer. The fourth one says, give me an eighth of a beer. And the bartender says, fuck, I hate you guys, and just pours 2 beers. In other words, my claim is that this infinite addition problem is equal to 2. How on earth could we know that? The trick is to look at what are called partial sums. I look at the sequence of finite addition problems called partial sums of S. So if S, capital S, is the big full addition problem, then I would say that the 0th partial sum, S0, is just 1. The first partial sum is 1 plus 1/2. The next partial sum is 1 plus 1/2 plus 1/4. The next partial sum is 1 plus 1/2 plus 1/4 plus 1/8. I'd like to compute these and see if we can't find a pattern. Let me get rid of some of this stuff. Just come back here. The next one I'll write down and then we'll compute them is S4 Okay, so let's pull up some Desmos and help ourselves to a little bit of a calculator. Yeah, I can do it here. It's fine. So 1 plus 1/2, 1 plus 1/2 plus 1/4, 1 plus 1/2 plus 1/4 plus 1/8, 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and that plus 1/32. And let's write these as fractions. So this first guy is 3/2. I'm going to just write these down and then I'll come back to my page. The next guy, oh wait, sorry, this first guy here was 1. The next guy was 3/2. The next guy was 7/4. The next guy was 15/8. The next guy was 63/32. Okay. So the first partial sum here was 1, then 3/2, then 7/4, then 15/8, then 63/32. Do you notice any patterns here? This is 4 minus 1/2, 8 minus 1/4, 16 minus 1/8, 64 minus 1/32.
I think you skipped 1/16.
Did I skip one? Oh shit, let me see. That's 31/16. Yeah. Plus 1/16 is in there. Sorry. So I did. I skipped over S4. So the question I want to ask though is still okay. Do you notice these numbers getting closer and closer to anything? Maybe if I put them back in their decimal form. Do these appear to be getting closer and closer to any particular number?
2.
Yeah. And remember how the joke goes, the bartender pours 2 beers and says, fuck, I hate you guys. So somehow, if you add 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 all the way out to infinity, that should be equal to 2, because as you give more and more and more terms to the sum approaches 2. So this is where that concept of convergence that I mentioned a minute ago comes in. If S is an infinite series, some say from 0 to infinity of 1/2 to the n, which is what we were just looking at, then this should be equal to this guy as n goes to infinity. And there's a special notation for that. It looks like this. This object right here is Sn. Now, if this notation is scary looking to you at the moment, don't worry. What I'm going to do is cook up a general result for infinite geometric series, but not today. That's a little bit more than we need for today. What I want to do for today is talk about just this thing. So again, we said here that S0 was 1. S1 is 1 plus 1/2, which was 3/2. S2 was 1 plus 1/2 plus 1/4, which was 7/4. S3 was 1 plus 1/2 plus 1/4 plus 1/8, which was, what was that? Did I write that? Yeah, 15/8. And I want to take a guess at what Sn is. Here's how I'm going to do it. 3/2 is 4 minus 1 over 2. 7/4 is 8 minus 1 over 4. 15/8 is 16 minus 1 over 8. I can write these in terms of powers of 2. This is called a limit, and it's not a notation that we've talked about. So don't stress too much, but it means I'm going to plug in really big numbers for capital N, bigger and bigger and bigger capital numbers for capital N, and see if this whole thing, as capital N gets bigger and bigger, gets closer and closer to any particular number. So another way to write this is just as the limit as capital N goes to infinity of S sub capital N. So it's that convergence thing that I talked about a minute ago with sequences, where the dots are all getting closer and closer to some number. That number L that the dots were all getting closer and closer to would be the limit of the sequence. That's the formal notation. But again, you're not officially responsible for that. I just kind of wanted to show you the symbols. Okay, so I want to come back here. 3/2 is 4 minus 1 over 2. That's 2 squared minus 1 over 2 to the 1. 8 minus 1 over 2 is 2 cubed minus 1 over 2 squared. 16 minus 1 is 2 to the 4 minus 1, and then 8 is 2 cubed. So what's the pattern here? S1 is 2 to the 2 minus 1 over 2 to the 1. S2 is 2 to the 3 minus 1 over 2 to the 2. S3 is 2 to the 4 minus 1 over 2 to the 3. Sn in general here appears to be 2 to the n plus 1 minus 1 over 2 to the n. I claim that this is true, and that I can use this to come up with the value of the full infinite series. To do that, I'm going to graph this. I'm going to look at this guy for very, very large numbers. What you'll notice is that the top is about twice as big as the bottom. Right? This is like 2 to the n plus 1. This is like 2 to the n. So these are very, very close to each other. It's just that the top, you multiply the bottom by 2 and then subtract 1. So I claim if you look at this sequence, its graph will be getting closer and closer and closer and closer to the line y equals 2 as we move further and further and further out. And the last thing I'm going to do for you today is demonstrate that. So there's a pre-made page here that is useful to invoke. Okay, ignore what's written here just for the time being. I'm going to play with this for a second. Whoop. Why is that jumping down out of the exponent? Whoa, 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 whoa. No, 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 no. Yes, like this, and then divide by 2 to the x. And I want to graph these points. Oh, and I want to zoom way in. Oh no, I am zoomed way in. I want to zoom way out. But not that. My horizontal. Let's just go from -1 to like 1. Okay. So here's the graph of the sequence Sn that we were just playing with. 2 to the n plus 1 minus 1 over 2 to the n. As I let n get larger and larger and larger, you'll see these dots get close to the line y equals 2, and then they stay there. if I add in the line here, y equals 2, this is exactly that behavior that we discussed here, right? These dots getting closer and closer and closer to this line. This is what we mean to say that this object, whatever it is going to L as n goes to infinity. So Sn here is definitely going to 2 as n goes to infinity. Which means if you add 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16, and you go all the way out to infinity, you add infinitely many of those terms together, you really do get 2. In whatever way you can make sense of it, if there's any way to make sense of adding that infinitely many things together, these particular things, 1 over 2 to the n, will add up to 2 for precisely this reason. So next time I'm going to give you a formula for the nth partial sum of a geometric series. I'll define what a geometric series is. It's just a series, an infinite sum, made up of geometric sequences inside. And I'll show you how to figure out when these come out to something finite and when they don't. You can imagine plenty of times these do not come out to something finite. But I'll tell you how to detect when they do. And then in the cases where they do come out to something finite, I'll tell you how to figure out what that finite thing is. It's very, very exciting. And that will be our last class on Wednesday. Also, again, on Wednesday, I'll be handing out your take-home exam. That exam is just going to cover the material since exam 2. So it'll cover just the things we've done after logarithms, which will be the sequencing theory stuff that we're talking about here, but also the systems of equations and matrices stuff that we did last week and the week before. So please work on wrapping up those homeworks. If there's any of the old homeworks that you have not done, please get them done ASAP. And then start on this last assignment in WebAssign, which doubles as the homework for sequences and series, and also your study guide for exam 3, or your quiz for exam 3. Again, exam 3 take-home test. I'll hand it out at the end of class next time. It'll be up on Canvas. There will be very clear directions there. You'll hand that in on the day of your final. And just one more time to say it, the final exam for this class is December 7th, which I believe is a week from today. Yep, next Monday. And it's at 3:30 p.m. Now that will be a proctored exam, right? That will be an exam that is done just the same as our previous 3 exams. It'll be in Canvas using honor lock. It'll be longer than the rest of the midterm exams, but also you'll have more time to do it. You'll have a full 2 hours. The final is comprehensive, covers everything from the whole semester. Yeah, that is it. So next time we'll talk a little bit more about sequences and series. I'll show you how to sort out the sum of an infinite geometric series, and that will be the end of the class. We can also spend time on Wednesday reviewing if there are any particular problems that you want to work with. And I'll probably schedule at least 1 extra office hour between now and the final. The final exam is, Monday, December 7th at 3:30 p.m. 3:30 to 5:30. It's in the syllabus and it's up on the website on Canvas. Make sure you put at least 1 thing in your phone to remind you, like at least 1 little alarm or something. Alrighty, guys, I'm gonna leave it here for today. If you have anything else you want to talk about, you can come see me in office hours. You can send me a message on Canvas or email. All of those are good. If you're nervous about your grade, I understand that things are difficult right now. A lot of people have been having a hard time deciding whether or not they want to stay in the class, withdraw from the class. If you're nervous about that, please have a conversation with me about that stuff before this Friday. I can help you before Friday. I cannot help you after Friday. After Friday, it's all out of my hands, has to go through petition committee. But before this Friday, I can help you out. If you want to do a review, if you can get a few people together that would like to do a review session for this class before the final, I'd be happy to help with that. Just talk to some of the other people in the class, find a day and time that would work for a bunch of you, and I'll arrange a big review session before the final. All right, we can talk more about that next time. I got to get running to my office hours. Hope you guys have a lovely rest of your afternoon, and I will see you on Wednesday.